the idea of space. It feels empty, really empty. You look up at night, you see stars, you see galaxies, but between them, just blackness, deep, endless black. It seems like nothing is there. A vacuum, a perfect void. That's what most people think. It's a natural thought. Our own planet, our solar system, it has things in it: planets, moons, asteroids, gas. But then you get out past the solar system, out past our galaxy. What's left? Just the big gaps, the spaces between the galaxies. We call them voids, we call them empty. But here's the thing, they are not truly empty, not at all. It's a common misunderstanding. The universe is tricky, it plays with our senses, things look one way, they are actually another way. The voids are a great example of this. They are far from perfect vacuums, they hold a lot of stuff. Just not stuff we can easily see, or stuff that is dense. That's the key. Density, or the lack of it. Think about it this way. Imagine a huge, huge room, gigantic, and you put a single grain of sand in it. Is the room empty? Mostly, yes, but that one grain of sand is still there. It's matter. Now imagine a whole lot of these rooms, and each has a tiny speck of something. That's closer to what the universe is like, especially in the voids. There's stuff, just spread incredibly thin. So thin, it's almost impossible to picture. What kind of stuff are we talking about? A lot of different things. Some are familiar, some are strange, some are still a big mystery. Let's start with the familiar. Gas. Yes, gas is out there, even in the voids. It's not like the air we breathe. Not dense at all. This gas is mostly hydrogen, the simplest element. It's what most of the universe is made of. And helium, the next simplest. These two elements were cooked up right after the Big Bang. They've been around ever since, floating through space. Some of it clumped together to make stars and galaxies. But a lot of it didn't. A lot of it stayed spread out, very, very spread out. This gas is called the intergalactic medium, or IGM for short. It's the material that sits between galaxies. Even the regions we call voids have some of this IGM. It's incredibly dilute, way, way less dense than anything we can make in a lab here on Earth. Like many millions of times less dense. If you could scoop up a cubic meter of this void gas, it might have just a few atoms in it. Compare that to the billions of atoms in a cubic meter of air. It's a huge difference. So, how do we know it's there? We can't see it directly. It doesn't glow bright enough. Not usually. But it does interact with light. Light from very distant, very bright objects. Like quasars. Quasars are super bright centers of young galaxies. Their light travels across billions of light years to reach us. On its way, that light passes through all sorts of stuff, including the gas in the void. When the light hits these hydrogen atoms, some of it gets absorbed. Specifically, certain wavelengths of light get absorbed. It's like a barcode. Each element leaves its own unique signature in the light. When we look at the spectrum of light from a distant quasar, we see these absorption lines. They tell us there's hydrogen in the way, and they tell us how much and how far away it is. These lines are called the Lyman alpha forest. It's like seeing a forest of tiny trees, each one an absorption line from a cloud of hydrogen gas. This is how we map out the gas in the intergalactic medium, even in the voids. Why does it matter that there's gas in the voids? This gas is the raw material for everything. It's the fuel for future stars and galaxies. DC'sman, leftovers from the Big Bang. It shows us how matter is distributed in the universe. It helps us understand how galaxies form and evolve. They don't just exist in isolation. They are constantly interacting with this intergalactic gas. They pull some of it in. They push some of it out. The voids are like big reservoirs of this important cosmic fuel. This gas isn't just one type. It's not all cold and neutral. Some of it is hot, really hot. We call it the warm-hot intergalactic medium, or WIM. This gas is so hot that its electrons have been stripped away from the atoms. We call that ionized gas. It's millions of degrees. How did it get so hot? When galaxies form, they're messy. They throw out a lot of energy and a lot of gas. Supernovae, which are exploding stars, blast material outwards. Active black holes at the centers of galaxies also shoot out powerful jets. All this stuff heats up the surrounding gas. It pushes it around. Some of this hot gas escapes the galaxies. It goes into the intergalactic space, into the voids. This WIM is very hard to detect. It doesn't glow much in visible light, but it does emit X-rays, very faint X-rays. Space telescopes designed to see X-rays can sometimes pick up signs of it. And again, it can absorb light from even brighter X-ray sources behind it. The presence of WIM matters because it's a huge component of the universe's normal matter budget. If we only counted the stars and galaxies, we'd be missing a lot. The WIM helps us account for that missing matter. It tells us about the energetic processes that heat up gas in the universe. It tells us about the outflows from galaxies, how they recycle matter and energy. So, it's not just emptiness, but an active, hot environment, even if it's very thin. So, gas is a big one. But there's more. What about dust? Yes, even dust. It's not much. Even less than gas. But it's there. Dust particles in space are like tiny bits of soot or rock. They are made of heavier elements cooked up inside stars, things like carbon, silicon, oxygen, iron. When stars die, they release these elements. Some of these elements condense into dust grains. These grains float around, some stay in galaxies, some get ejected into the intergalactic space. Again, very, very sparse, but present. Dust interacts with light too. It can block light. It can scatter light, it can also absorb light and then re-emit it at longer wavelengths, like infrared. This is how we know it's there, even if it's very little. Over vast distances, its effects add up. Infrared telescopes can detect this faint glow from coal dust. It's still incredibly sparse in the voids. Much of it tends to be closer to galaxies, but some inevitably drifts out into the intergalactic space. Its presence, however slight, reminds us that the voids are not pristine nothingness. They contain the heavy elements forged in stars, the building blocks of planets. So, we've got gas and dust. They are both made of what we call normal matter, the stuff that makes up everything we can see and touch. But normal matter is only a small part of the universe. The biggest thing in the voids and everywhere else is something else entirely. Something invisible. We call it dark matter. This is where things get really weird. Dark matter doesn't shine, it doesn't absorb light, it doesn't reflect light, it doesn't interact with light at all. So we can't see it directly, but it has gravity, lots of it. We know it's there because of its gravitational pull. We see galaxies spinning too fast. They should fly apart. But they don't. Something invisible is holding them together. That's dark matter. We see galaxy clusters that are much more massive than the visible stuff suggests. That's dark matter. We see light bending around massive objects in a way that implies a lot more mass than we can see. That's gravitational lensing, and that tells us about dark matter. Dark matter is not just clumped in galaxies. It forms a kind of scaffolding, a cosmic web. Imagine a giant, three-dimensional spider web. The galaxies sit in the thickest strands and knots of this web. The voids are the huge, empty-looking spaces between the strands. But even in these voids, the web is still there, just much thinner. Dark matter is spread out everywhere, including the voids. It's just less dense there, but it's still the dominant form of matter in the universe. So, even if a void looks empty, it's actually filled with a huge amount of invisible dark matter. We don't know exactly what dark matter is. We have theories, new particles, but we know it's there. And it's in the voids. How do we know it's in the voids? We detect it through its gravity. One major way is through gravitational lensing. Imagine light from a very distant galaxy. As this light travels to us, it passes by massive objects. These massive objects, because of their gravity, bend the path of the light. It's like a lens, a giant cosmic lens. The light gets distorted, the distant galaxy looks stretched or smeared. By measuring how much the light is distorted, we can figure out how much mass is doing the bending. And very often, the amount of bending implies far more mass than we can see. That extra invisible mass is dark matter. We use this technique to map out dark matter. We see it clumped around galaxies. We see it in the filaments of the cosmic web, and we see its influence even in the voids. The voids are just regions where the dark matter density is much lower, but it's not zero. The cosmic web, made mostly of dark matter, extends through the voids. It's like a ghostly scaffolding. So, when we look at a void, we are actually looking at a vast region filled with invisible mass. Mass that has a gravitational pull. This pull subtly shapes the void. It influences any gas that's present. So dark matter is a massive invisible occupant of the voids. Why does dark matter in voids matter? Because it tells us about the fundamental properties of dark matter. If dark matter were different, say, if it interacted more strongly, it might not be so smoothly distributed. It also tells us about how the cosmic web formed. The voids are an essential part of that web. Understanding the voids is key to understanding the structure of the entire universe. And then there's an even bigger mystery, dark energy. This is what's making the universe expand faster and faster. It's not matter. It's more like a property of space itself. It pushes space apart. It's thought to be smoothly spread throughout the universe, everywhere, including the voids. In fact, it's in the voids where dark energy's effects are most noticeable. Why? Because voids have less matter and dark matter to counteract its push, so the voids are expanding even faster than the denser parts of the universe. Dark energy doesn't just fill the voids, it actively shapes them. It makes them grow. It's the engine driving the universe's accelerated expansion. Again, we don't know what it is. We just know its effects, but it's certainly not nothing. How do we study dark energy in the voids? By studying the sizes and evolution of the voids themselves, by looking at how the cosmic web structure changes over time. We can compare observations of distant, older voids with closer, younger ones. We can measure how fast they are expanding. This helps us constrain the properties of dark energy. What is its density? Does it change over time? The voids are like giant laboratories for dark energy. They are crucial for understanding this fundamental force that dominates the fate of our universe. So, we have gas, dust, dark matter, and dark energy. That's a good start, but there's more. Think about particles, tiny, fast-moving particles. Cosmic rays are one example. These are high-energy particles, mostly protons, also some atomic nuclei. They come from extreme events in space. That's exploding stars called supernovae, are a big source. Active black holes can also accelerate them. These particles travel through space at almost the speed of light. They can zip through galaxies. And they certainly zip through the voids. They are very sparse, but they are there. Constantly flowing through the vast emptiness. We detect them when they hit Earth's atmosphere, or with special detectors on satellites. They are another component of the empty void. How do we know they are in the voids? We detect them when they hit Earth, or our satellites. We trace their paths. We see that they are coming from all directions. They have traveled through vast stretches of intergalactic space. Some of that space must be voids. Their presence tells us about the most energetic processes in the universe. It tells us that space, even empty space, is not a quiet place. It's bombarded by these high-speed projectiles. They are a subtle but persistent component of the voids. Then there are neutrinos. These are truly strange particles. They are tiny, almost no mass. They interact very, very weakly with other matter. They pass through pretty much everything. Billions of them pass through your body every second, without you ever feeling a thing. They come from the sun, from nuclear reactions in stars, from supernova, and from the very early universe, a cosmic neutrino background. These neutrinos are everywhere, absolutely everywhere, billions and billions of them in every cubic centimeter of space. Even in the voids. They are a constant, invisible torrent. They definitely count as something. And they are in the voids. We detect neutrinos with very special detectors, often huge tanks of water or ice deep underground. We wait for a very rare interaction to happen. It's incredibly hard, but we do it. Their omnipresence means that even the voids are teeming with these elusive particles. They may not interact much, but they have mass, however small, and they are part of the universe's fabric. So, the voids are not empty of these ghost particles. What else? Light itself. Photons. Even if a void looks dark, light is still traveling through it, light from distant galaxies. Light from the cosmic microwave background, or CMB. The CMB is the leftover radiation from the Big Bang. It's everywhere. It fills the entire universe. It's a faint glow of microwaves. It's the oldest light we can see. And it's flowing through every single void. So even when we talk about darkness, there's always light, however faint, making its way through. Photons are particles, so voids are filled with photons too. Beyond the CMB, there's also the light from all the distant galaxies. Billions of galaxies. Their light is constantly traveling through the voids. Most of this light will miss any matter in the void. It will just keep going. But it's still there, passing through. So, in terms of photons, the voids are far from empty. They are permeated by the universe's entire history of light. And what about gravity? Gravity isn't just something that objects have. It's a property of space and time itself. Big events in space, like black holes crashing into each other, or massive stars exploding, create ripples in space-time. These are called gravitational waves. They travel out from their source at the speed of light. They pass through everything, including the voids. They stretch and squeeze space ever so slightly as they go by. We've started to detect these waves here on Earth, so the voids are also filled with these invisible ripples of gravity. These are ripples in the very fabric of space-time. They are caused by huge cosmic events. Things like black holes merging or neutron stars crashing together. These events create disturbances that travel outwards at the speed of light. They pass through everything, including the voids. We've only recently been able to detect these waves directly. It's a brand new window into the universe. Their presence in the voids means that even space and time themselves are being subtly stretched and squeezed by these cosmic tremors. The voids are not immune to these fundamental vibrations of reality. We also think there are very weak magnetic fields in the voids. Where do they come from? That's still a bit of a mystery. Maybe they were generated in the early universe. Maybe they are seeded by active galaxies and then spread out. These fields are incredibly weak, much weaker than the Earth's magnetic field. But they can influence cosmic rays, they can affect how gas cools or heats. They are another subtle component of the voids. Another layer of something where we once thought there was nothing. So when we say voids, what exactly are we talking about? They are not just random empty spaces, they are structured. The universe isn't just a random sprinkle of galaxies. It has a large-scale structure, it looks like a giant sponge, or a cosmic web, as mentioned before. There are vast filaments and sheets of galaxies. And then there are these huge underdense regions in between them. These are the voids. They can be hundreds of millions of light years across. They are the biggest structures in the universe. They take up most of the universe's volume. Think about the largest superclusters of galaxies. They are like the knots in the web. The filaments connect them. The voids are the spaces between these threads and knots. Even though they are called voids, they are still part of this overall structure. They are not disconnected. They are just the emptiest parts of a mostly empty universe. The density of matter in a void can be 10 times less than the average density of the universe. That's a huge difference, and these voids are growing as dark energy pushes the universe apart. It makes the voids bigger. The galaxies are moving away from each other. They are moving into the filaments and away from the centers of the voids. So the voids are becoming even emptier in terms of normal matter and dark matter. But the dark energy density stays constant. It just keeps on pushing. How do we even find these voids? We map out the universe. We look at billions of galaxies. We measure their positions in 3 dimensions. We see how they cluster together. And then we see the huge gaps where there are very few galaxies. That's how we identify them. It's like looking at a huge map of cities and towns. You see where the cities are dense, and then you see the wide open spaces in between them. Those are the voids of the universe. The study of these voids is actually very important. It tells us a lot about the universe. For example, the way voids grow in their sizes can help us understand dark energy better. How strong is it? How does it behave over time? The distribution of dark matter in and around voids also tells us about its properties. It's not just about what's there, it's about what's not there, or how little of it there is, and how that affects the whole cosmic picture. The universe began very uniform, almost perfectly smooth, but it wasn't perfectly smooth. There were tiny ripples in density. Some places were a tiny bit denser, some were a tiny bit less dense. Over billions of years, gravity took hold. The slightly denser regions pulled in more matter. They grew. They became the filaments and galaxy clusters. The slightly less dense regions gave up their matter. It flowed away, drawn into the denser parts. These regions became the voids. They emptied out. But they didn't become completely empty. They just became very underdense. So, when we talk about voids, we're talking about regions of space where the density of matter is much lower than the cosmic average. But critically, it is not zero. It's not nothing. It's just very, very little of something. It's like comparing the air at sea level to the air high up in the mountains. Both have air, but one is much, much thinner. The voids are the thin air of the universe. Think about the implications of this. It means that even the empty parts of the universe are active. They are dynamic. They are evolving. They are full of things that shape the universe. Dark matter is flowing through them, and dark energy is expanding them. Cosmic rays are zipping through them. Neutrinos are constantly passing through them. Faint light from distant objects is traveling through them. It's a busy place, even if it looks utterly desolate to our eyes. The human mind naturally tries to categorize things full or empty, light or dark, here or not here, but the universe often works on a spectrum, not a simple binary. The voids are not empty, in the sense of a perfectly sealed container with absolutely nothing in it. They are empty in the sense that they are the least dense regions of a universe that is mostly low density anyway. It's a relative emptiness, not an absolute one. And our understanding of these voids is always getting better. New telescopes, new theories, better computer simulations. We can run simulations of the universe's evolution. We can start with the initial conditions from the Big Bang. Then we let gravity and dark energy do their work. These simulations naturally form the cosmic web. They show the filaments, the clusters, and the voids. And they show that even the voids are not empty of dark matter, of gas, of dark energy. They confirm what our observations tell us. So next time you look up at the night sky and you see that blackness between the stars, between the galaxies, remember this. It's not truly empty, it's not a perfect void, it's a vast expanse, yes, a desolate one maybe. But it's also filled with a complex, dynamic mix of gas, dust, dark matter, dark energy, cosmic rays, neutrinos, light, and even ripples in space-time. It's a low-density environment, an underdense region, but it's not nothing. It's a crucial part of the universe. It's where the story of the universe's expansion truly plays out on the biggest scales. It's a testament to how much we've learned and how much more there is to learn about what seems to be nothing at all. This understanding changes how we think about space. It makes space less of a static backdrop. It makes it more of an active player. Everything in the universe is connected, even the parts that seem separate. The voids are not isolated pockets of nothingness. They are integral to the grand structure of the cosmos. They are part of the cosmic tapestry. A very thin part, but a part nonetheless. We often imagine space travel as going from one bright star to another, or from one glowing galaxy to another. But most of that journey would be through these empty voids. And on that journey, a spacecraft would still be bombarded by cosmic rays. It would still be bathed in the cosmic microwave background. It would still be passing through invisible fields of dark matter. It would still be expanding away from its destination due to dark energy. It would still be interacting with the sparse atoms of hydrogen and helium. These are all subtle effects, yes. But they are present. They are real. The word empty implies a complete lack of anything. A perfect vacuum. We can achieve very good vacuums in labs on Earth. We can remove almost all the air. But even those vacuums still have some particles. Even a so-called perfect vacuum, in theory, would still have quantum fluctuations. Tiny bursts of energy and particles appearing and disappearing. So even the idea of absolute emptiness is hard to achieve, even on the smallest scales. On the cosmic scale, empty is a misnomer. It's a simplification. A void is not devoid of everything. It's just devoid of high concentrations of things. It's a region where gravity has pulled things away, where cosmic expansion has thinned things out. It's an arena where the fundamental forces of nature are still at play, even with so little visible matter. Think about how amazing it is that we can even detect these things. The gas, the dust, the dark matter. It's like finding invisible clues in a huge dark room. It takes incredible technology. It takes clever thinking, it takes looking for subtle effects, it takes building giant telescopes on Earth and in space. It takes learning how light behaves when it travels for billions of years. It's a triumph of science to unravel these mysteries. To show that empty is not the right word, our journey to understand the universe is really a journey to understand its components. All of them. Even the parts that are hard to see, even the parts that don't shine. The voids teach us about the subtle dance of gravity, dark matter, and dark energy. They teach us about the leftover ingredients from the Big Bang. They teach us about the constant flow of energetic particles. They teach us that there's always more than meets the eye, or in this case, more than doesn't meet the eye. So, to wrap it up plainly, the spaces between galaxies are not truly empty. They are very, very sparse. They have extremely low densities of matter and energy, but they are not nothing. They contain gas, extremely diffuse hydrogen and helium, some of it neutral, some hot and ionized WIM. This gas is the fundamental building block of the universe, left over from the Big Bang and continuously recycled by galaxies. Dust sparse, microscopic grains of heavier elements ejected from stars. Dark matter, the dominant form of matter, invisible, only detected by its gravity. It forms a cosmic web that pervades the voids, albeit at lower density than in galaxy clusters. Dark energy, the mysterious force causing the universe's accelerated expansion. It fills all space, including the voids, and actively makes them grow. Cosmic rays, high-energy particles from supernovae and other extreme events, zipping through space. Neutrinos, tiny, almost massless particles created in stars and the Big Bang that pass through almost everything. They are incredibly numerous throughout the universe. Photons, light particles, including the omnipresent cosmic microwave background radiation from the Big Bang, and faint light from distant galaxies. Gravitational waves, ripples in space-time caused by cataclysmic cosmic events traveling through the voids. Magnetic fields. Very weak, large-scale fields whose origins are still being researched, but which pervade the intergalactic medium. This list isn't just about presence, it's about fundamental forces in particles. It's about the very fabric of existence. The voids are not inert regions, they are part of the active, evolving cosmos. They are dynamic. They are shaped by gravity. They are expanded by dark energy. They are traversed by particles and waves. It's a powerful reminder that our intuitive understanding of the world, based on our daily experiences, often falls short when we look at the universe on its grandest scales. What looks like empty space to us is, in fact, filled with a complex, intricate tapestry of invisible forces and particles. The true emptiness is far more theoretical than real. The voids are not empty, they are just incredibly diluted. And that dilution is part of their story, a very important story in the grand scheme of the universe. It challenges our simple definitions, it forces us to think bigger, it forces us to think beyond what we can immediately perceive. And that's what science is all about, understanding the unseen, understanding the subtle, understanding the truly vast. The voids are a perfect lesson in this. They teach us that even in the vast nothingness, there is always something.